There's stuff about supply and demand in here, but we're not going to talk about supply and demand. You may be happy to know. What we will talk about instead is bank accounts, or more generally, future and present values of ultimately income streams. What's an income stream? Well, perhaps the nicest way to imagine an income stream is money flowing into your bank account every second of every day, which if you have a YouTube channel like me, technically does happen. Well, not quite. It doesn't actually go into my bank every second of every day. It goes into my Google account every second of every day. And then I deposit it into my bank once a month. But it's not much, right? And I think I've told some of you, I'm making like $6 a day with over 1,000 videos, $6 a day. Right now, I'm trying to make it go up. That comes out to like almost like $200 a month almost. So it's nothing to be too sad about, but $6 a day, that's like 25 cents an hour. It's not quite 1 cent per minute, right? So anyway, before we think about the time value of income streams, let's think about bank accounts. Recall the compound interest formula. In its most general form, and we're not really going to use the most general form, but I want to mention it, is that your future balance, which sometimes people call A for accumulated value, but our book calls it B for balance, future balance, is the principal, which is how much you deposited. You could call it present principal, and this kind of principal is spelled P-R-I-N-C-I-P. I always have to think about it. A-L. The L-E principle is like a principle of math or a principle of science. That's an L-E kind of principle. A-L kind of principle is this kind of principle, or like a principle in a school. Times 1 plus, in the more general form, you've got a certain number of compounding periods per year, call it n, to the nt power. So t is time. By the way, you don't always say present principal. Sometimes you just say principal. But actually, p is also going to represent a present value, so it's not a bad thing to put it there. T is time, typically in years. So I'll go ahead and assume it's in years. It doesn't have to be in years, but typically it is. R is called the nominal interest rate. And if time is in years, it's, well, I should have added the word annual in here. Nominal annual interest rate. If time were in months, then it'd be the nominal monthly interest rate. And N, which occurs in 2 spots, here and here, is the number of compounding periods per year. The number of times you get interest accrued to your account every year. Compounding periods per year. Most bank accounts compound 4 times a year, N is 4, quarterly, which is every 3 months. Some bank accounts compound monthly, N is 12. Actually, my old TCF account in recent years compounded monthly, then it got switched to Huntington, and now they compounded quarterly. Monthly is a little bit better, although, right, we're talking in these days, interest rates that are so low, you might get a couple cents, and it really doesn't matter much. Another funny story, when I was, well, a little younger than you, I had a bank account in the early 80s that had an 8% interest rate. I am not lying. Of course, there were downsides back then. For one thing, mortgage rates right now for houses are very low, 2 or 3% or so, although they're going up because inflation is going up. Back then, mortgage rates were like 15%. Yeah. Inflation was really bad back then too, just like it's getting bad now. So maybe your bank accounts are going to start getting better interest because inflation is getting so bad. Maybe. Can't know for sure, I don't think. I mean, the Federal Reserve is raising interest rates. I think they will go up. How high, I don't know. Probably not 8%. So that's how you use this formula. You plug in your principal, like $100, say, or $1,000. Your interest rate, if it is like a 0.1%, you'd plug in 0.001. It'd be very small for R. If it's compounded quarterly, you'd plug in n equals 4. And if you leave it there for 10 years, you'd plug in t equals 10. And at current interest rates on $1,000, you might get $1 of interest after 10 years, maybe. At 8%, you get a lot more than that. Okay, so that's the background. However, what we want to do in this chapter, in this section, 8.6, is we want to apply this formula more generally than just bank accounts. Like to what? Crypto? Well, you could. Stocks? Well, you could. However, if you do apply it to crypto or stocks, it's not going to work as well because those are more volatile. Their value goes up and down a lot more. It's not just like a bank account always going up. It would be more of an approximation in that situation. But even more generally, we can apply it to modeling the entire economy, though it would be a very simplistic model. And we can also talk about something called the time value of money. Money has a time value, whether you think about bank accounts or not, whether you even think about investments or not. Why? And what does that mean? The most basic way to describe the time value of money is that most people, there could be exceptions, most people would probably prefer $1 today than $1 a year from now. If I say, I'll give you $1 today or $1 a year from now, you'd probably take the $1 today. You have a preference for the money right now. Why? Well, maybe you're thirsty. Maybe you want to go buy a pop. Okay, right now. You don't want to wait a year. That's one reason. Another reason is, well, you're like, well, I might as well just take the $1 right now. Why wait a year? Inflation's another reason. $1 a year from now is probably going to have less purchasing power. You won't be able to buy as much. However, on the other hand, maybe if somebody offers you this deal, you are indifferent. I'll either give you $1 today, or in 1 year, I'll give you $1.08. Now, it's such a small amount, you might say, well, I'll just go ahead and take the $1 today. But if it were a larger amount, like $1 million right now, or $1.08 million a year from now, which would be $1,080,000 a year from now, you'd probably wait a year. Or maybe you'd be indifferent. Maybe you'd be, either way is okay. You have no preference. So it's in that kind of broad scheme of things that we could try to model the time value of money with similar equations. Though what you do is you typically take the n to be 1 when you do. Why bother with compounding, when you're just trying to model the broader economy or the time value of money? I mean, you could think about compounding if you wanted to, but you don't have to. And the compounding really comes into play because the bank is just giving you money every quarter or every month or something. And by the way, that's partially why this is called a nominal interest rate. It's different than the actual amount of interest that you earn, which is called an effective interest rate. Don't worry about details. So with the time value money, we typically take n to be 1. And now let's think about a few different scenarios. Let's also let P equal 1, so we'll think about $1. Let's take R to be, say, 8%, which you'd want to enter in the formula as 0.08. This is 8%. And let's take T to be 1 as well. So with the time value money, you always take n to be 1. When we're thinking about different scenarios, you don't always use these particular numbers. You might use different numbers here. Based on this scenario, based on $1 today, this is representing $1 today in the present, I could ask, what is the future value of that $1 in 1 year based on this interest rate? The future value of the $1 1 year from now would be what I get when I plug those numbers into this formula, taking n to be 1 as well. It would be B equals 1 times 1.08 to the first power, which would be $1.08. And if in your modeling, the 8% interest rate seems like a reasonable model to use, which is probably actually a good idea right now because inflation was about 8% for the past year. What you're saying is these amounts, $1 today and $1.08 a year from now, are equivalent to each other. I am indifferent in my choice. Would I rather have $1 today or $1.08 a year from now? It doesn't matter to me if this model is accurate. I'm not saying the model is accurate. I'm just saying if it's accurate, then you'd be indifferent. These be equivalent amounts. I can also switch it around. Just give me another 2 minutes here. So what we're doing here is we're thinking about B equals P times 1 plus R to the T power, n is 1 here. I could switch it around and I could solve for P. I could divide both sides by 1 plus R to the T. I could write P is B divided by 1 plus R to the T, which you could also write as B times 1 plus R to the negative T. And so instead of the $1 today being pushed into the future to $1.08 a year from now, I could ask, what's the present value of $1 1 year in the future? What's the value of that today? The present value of $1 in 1 year is its value today, which is going to be less than $1. Use this formula. The B now is 1 instead of the P being 1. 1 times 1.08 to the negative 1 power. And that's going to be less than 1. 1.08 to the negative 1 power. Which I hope you know, oops. I hope you haven't forgotten, that's the same as 1 divided by 1.08. It's about 93 cents, say. $0.93, which of course is 93 cents. So I'm also indifferent between those two amounts, $1 1 year from now and 93 cents today. We call this the future value. We call this the present value. And what we're going to get into on Monday is thinking about these kind of things in the context of income streams. And that's where you have to do some integrals. You can read about it ahead of time. All right, see you then.